Separation of mixtures of CO2 and C2H6 is relevant in the context of natural gas processing. Current technologies for CO2 C2H6 separations use extractive distillation because of azeotrope formation. In my presentation today, I'm going to discuss a different strategy for separating mixtures of CO2 from C2H6, and this strategy relies on anti-synergy between mixture adsorption and diffusion in microporous crystalline materials. In particular, I'd like to consider separations using DDR zeolite that consists of cages separated by narrow windows with an aperture size 3.65 angstrom. The shortest aperture distance and the longest distance is 4.37 angstrom. Both of these gas molecules jump lengthwise across the windows, and since the cross-sectional dimension of CO2 is smaller than that of C2H6, the mobility or diffusivity of CO2 is significantly higher than that of C2H6. Let's look at experimental data on transient uptake within crystals of DDR zeolite. The experimental data are shown by the symbols. The red circles are for CO2 and the blue squares are for the uptake of C2H6. At equilibrium, the loading of C2H6 is significantly larger than that of CO2. However, if you look at the initial transients, we note that the CO2 loading within the DDR crystals is significantly higher. This is because of the higher mobility of CO2. The pores are initially filled with CO2 before they reduce in the loading to reach the equilibrium value. So there is an overshoot in the CO2 loading during the initial transients. To model these experiments, we resort to the Maxwell-Stefan diffusion equations, and the expression to describe the transient uptake of the component loadings is described by this partial differential equation, where Qi is the molar loading of component I at any position R within the crystallite, which is assumed to be spherical, at any time t. This time derivative is related to the molar flux of species I, and the molar fluxes are described by the Maxwell-Stefan diffusion equations as being proportional to the gradient of the chemical potential of species I, and the proportionality constant is the Maxwell-Stefan diffusivity d sub I. Rho is the framework density of DDR. The experimental data can be matched taking the ratio D1 divided by D2, the ratio of the Maxwell-Stefan diffusivity of CO2 to the C2H6 to be 1333. And there is another parameter that is important, and that is the ratio of the Maxwell-Stefan diffusivity for component 1, which is CO2, divided by the square of the radius of the crystallite. And to match the experiments, we take the diffusional time constant to be 0.125 per second. I'll return to these parameters later in my presentation. So the mixture adsorption equilibrium favors C2H6, but the diffusion selectivity favors CO2, and we would like to cash in on the anti-synergy between adsorption and diffusion to achieve the separation of CO2 C2H6 mixtures in fixed bed adsorbers. For a feed mixture, say 50-50 CO2 C2H6, we would like to recover purified C2H6 in the adsorption phase. In other words, we would like the pores to selectively take up the more mobile component. So we need to achieve or realize kinetic separations. Let's summarize the adsorption and diffusion characteristics of mixtures of CO2 and C2H6 in DDR zeolite. We define the adsorption selectivity as the ratio of the component loadings of CO2 to C2H6 divided by the corresponding ratios of the partial pressures. The adsorption selectivity favors component 2, which is ethane. We define the diffusion selectivity as the square root of the ratio of the Maxwell-Stefan diffusivity of component 1 to that of component 2, that is CO2 to C2H6, and the diffusion selectivity favors CO2. So we have a scenario in which the adsorption selectivity is smaller than unity and the diffusion selectivity is larger than unity. In other words, we have anti-synergy between adsorption and diffusion. There is another parameter that is relevant to describe separations in fixed bed adsorbers, and that is the ratio of the Maxwell-Stefan diffusivity to the square of the crystallite radius. This is often called the diffusional time constant. This parameter quantifies the severity of diffusional influences. If this value is very large, there are no diffusional influences and it is impossible to achieve kinetic separations. So in order for kinetic separations to be realized, we need to have a high degree of diffusional influences, and this is achieved by choosing crystallite sizes that are relatively large. Watch also my presentation on synergistic mixture separations with MOFs and transient breakthrough simulations on my YouTube channel. Let us now move on to separations in fixed bed adsorbers and see how we can exploit the anti-synergy between adsorption and diffusion. I consider transient breakthroughs in an adsorber packed with a DDR zeolite. The feed mixture consists of an equimolar mixture of CO2 and C2H6 with partial pressures 20 pascals each, and the breakthrough simulations have been carried out for two sets of conditions. The two scenarios are shown here. The blue lines are the scenarios in which the diffusional time constant d1 divided by rc squared is 1.25 times 10 minus 3. The continuous blue line is for the breakthrough of C2H6, and the dashed blue line is for the breakthrough of CO2. So if we have strong diffusional limitation that is characterized by small values of this diffusional time constant, the component that breaks through first is C2H6. So this is the desirable scenario where we have kinetic separations dictated by diffusion that favors CO2, and CO2 is preferentially adsorbed. If, on the other hand, the diffusional time constant is significantly larger, say 0.5 per second, the breakthroughs are shown by the black lines. The continuous black line is for C2H6, and the dashed black line is for CO2. In this case, CO2 is the component that breaks through earlier. This is not a scenario that is desirable because we would like to have purified C2H6, leaving the adsorption cycle. So the message here is that for kinetically driven separations, we need to use crystallite sizes that are large enough to lead to significant diffusional influences. And in this set of calculations, they need to be lower in value than say those used in the uptake experiments. Watch also my presentation on what drives kinetic separations on my YouTube channel that discusses further details of the modeling of these breakthroughs for kinetic separations. All the modeling details are available in my publication in ACS Omega, published in 2019.